Okay, so a couple of announcements just before we begin. Sorry about that. It's a very temperamental projector. So first of all, the final lecture, Lecture 10, I sent an announcement to the mailing list, but just in case you didn't catch that, that will take place the morning of the 1st of April. So this isn't an April Fool, so if you thought this mail came to the list and you're thinking, I don't have to wake up that day, there really is going to be a lecture. I appreciate that that is outside the time where classes normally occur. As a result, this is an optional lecture, so it's going to be a lecture on games, case study on classic board games with reinforcement learning. I think it's interesting. It'll pull together a lot of elements of the course, but it's optional, so if you've already booked your time away and you can't attend, then don't worry, it's not going to affect your exam. But if you do have the chance to come along, it should be interesting, and I'll also mention that all of these videos will be made available online very shortly. So if you do miss anything, you can catch up online. Second announcement is the deadline for the assignment. So that will be the following day, April 2nd. So hopefully you guys have made a start on that. If you do have questions, please send them to the mailing list, because if you're wondering about something, probably means 10 other people have the same question, and so it's quite useful just to ping those backwards and forwards on the mailing list to just make sure everything's crystal clear. Okay, so let's get going. So today's lecture is on policy gradient methods. This is a very popular, widely used class of reinforcement learning methods. Again, we're in the part of the class where we talk about things which are actually used in practice to solve interesting, challenging reinforcement learning problems. So just to give an outline of how this is going to pan out, we're going to start off with an introduction where we'll understand roughly what's going on. And then we'll talk about, we'll focus in on policy gradient methods. So what's going on in this class is we're really talking about methods that optimize the policy directly. So instead of working in value functions, as we've considered so far, this is now about working with the policy. How can I see some experience, and from that experience figure out how to change my policy in a direction that makes that policy better? And what we'll do is we'll see a variety of different methods for doing this, which are all based on the simplest principle, if you like, for improving a policy, which is policy gradient. So we adjust the policy in the direction that makes it better. We follow the gradient. We'll consider 3 different ways to do that. We'll start off with a sort of naive but sometimes effective numerical approach by using finite differences. And then we'll move on to see that actually, for many of our reinforcement learning methods, there is an analytic formulation for the policy gradient. So despite what you might think, you can actually just have an agent which follows its trajectory, sees how much reward it gets along the way, but also knows which direction to adjust its policy so as to move it directly in the direction that makes its policy better. And finally, the most practical set of methods which we'll consider are the actor-critic policy gradient methods. So these are methods which combine everything from this class with everything from the previous class. So they work with both value functions and with policies and try to get the best of both worlds. Okay. So, introduction. So, last lecture, we had a lecture where we talked about value function approximation. We considered 2 different types of value function approximation. We considered approximating the state value function. So this is the true state value function, which tells us how much reward can I really get in this MDP in expectation if I follow this policy pi. So if I'm in some state S, what's the true expected reward I'll get from that point onwards? Or we had the Q function, which tells us for some state S and some action A, what's the true accumulated reward along some trajectory that I can get from that point onwards taking that action under this policy. So those are the ground truths, and what we did in the last lecture was we approximated those things using a function approximator, like a linear combination of features or a neural network. We tried to estimate this thing. We had some parameterized function, which had parameters w. We basically tried to fit this thing using ideas which are familiar from supervised learning. We tried to fit a function to this ground truth, so we started to understand the shape of how much reward can I get from different parts of the state space and different parts of the action space, respectively. But in that lecture, so last lecture, the policy which we then used when we actually wanted to do control, we didn't represent the policy explicitly. Instead, we just used the value function to pick actions. So once we got our function approximator for Q, that was enough to pick actions because we could just act greedily or perhaps epsilon greedily to pick the action which gets the most Q. So that was a very effective approach to control using function approximation. But it's only one approach to function approximation. And in some sense, more direct or sometimes more natural approach is to directly parameterize the policy, not the value function. So now we're going to have a different function approximator. We're going to have some parameters u. So in the last lecture we had w. So the difference between last lecture and this lecture is like whether it's w or u. And we're going to use these parameters u, and we're going to parameterize the policy now. So we're going to parameterize this distribution. Our policy pi is now going to be something we directly manipulate. So we control these parameters which affect the distribution by which we're picking actions. So think of this, if this was deterministic, which we'll consider later on, this could just be a function. The policy could just be a function. You know, which action do we pick in a given state? And now we learn the parameters which tell us, you know, for each state, which action should I pick? And so again, you could think of this as some arbitrary function approximator, like a neural network, where you plug in your state, and it tells you which action to pick, or a distribution over actions to pick. And so formally, this policy is going to be now a probability distribution over actions that's conditioned both on the state and our parameters. So we're actually defining probability distribution, and we're tweaking, we're learning how these parameters should change the probabilities by which we pick different actions in different states. And what we're going to do is try and understand how to modify this parameter vector u so as to solve the reinforcement learning problem, so as to maximize the amount of reward that we can get in this environment. And again, what we're going to do in this lecture is we're going to focus on model-free reinforcement learning. So we're really going to focus on how to throw down your agent, throw your robot into some maze, and this thing just wanders around, and just directly from experience, without anyone telling it the dynamics of the environment, it should be able to figure out how to adjust its parameters of its policy so as to get more reward from the environment. And in case it's not clear, the main motivation behind both of these methods is that we want to be able to scale. We want to be able to scale to large, interesting MDPs, large, complicated environments, in which it's not possible to separately for each distinct state say, oh, I'm going to take this action here in this state, and this action here in this state. So we need a function approximator. We need some parameters that sort of specify how, across this state space, we're going to modify these parameters. Apparently I spent too long on that slide. That was the power cable. So while we're waiting for my computer to come back to life, any questions? Hopefully it's, the motivation should be clear. So what we'll start to do now is to understand how we can actually take this parameterized policy with this parameter vector u and start to adjust those parameters so as to get more reward. And the main mechanism that we're going to consider is gradient ascent. In other words, how can we compute the gradient to follow so as to make this policy better? And if we can follow that gradient, we'll strictly be moving uphill in a way that improves our policy. If we know the gradient with respect to the total reward that we're going to get in this MDP, we're just going to follow that gradient in a direction that gets us more reward. And what we're going to do over the next few slides is formalize what that means, if my computer comes back to life, so that we can start to understand how to maximize reward. And we'll consider a few different ways that we can formalize this objective function. So before we do that, I'm going to ask something to you guys while we're waiting, which is, can you think of any advantages or disadvantages of using policy gradients compared to value-based methods? Like, why work with policy-based methods? And you'll think why it might be a better idea to work with policy-based methods than value-based methods. Good.
You need to store fewer things if you're working directly with the policy.
Right, so you might need to store fewer things. So why do you think you might need to store fewer things?
Because you don't have to store the value function or your approximation.
Right, so there are some situations where it's more efficient to represent the value, the policy, than the value function. There might be situations where, imagine you're playing one of these Atari games like Breakout or something, and it might be that the value function is quite complicated. It might be that actually precisely working out how much score you might get from some point onwards might be tricky, but to represent the fact that if the ball is coming down over here, you should always move left, might be a very simple policy to represent. Whereas actually working out precisely that you're going to get 1,714 points if you move left might be a much more complicated function to approximate. So there are cases where a policy can be more compact. So now we've got the slides back, I'm going to come back to this question here. So some other reasons why it might be a good idea to use policy-based reinforcement learning. So maybe the main one you'll see in the literature is that it has better convergence properties, that we saw that there are some cases where value-based methods can oscillate or chatter or even diverge if you do things in the wrong way. Whereas if you just follow the gradient of your policy, these methods tend to be more stable. You're smoothly updating your policy. You don't get these dramatic swings in what action you're going to take, because you just make a little incremental change to your policy and you move in the direction that makes your policy better. And so they tend to have better convergence properties, and indeed if you just directly follow the policy gradient, you're guaranteed to converge at least to a local optimum. Another big one is that these methods are effective in continuous action spaces or high-dimensional action spaces. With a value-based method, you have to work out how to compute the max. And I would say this is probably the number one reason to use policy gradient methods, is they circumvent the requirement to have this max. So if we're doing something like Q-learning, or indeed if we're doing something like SASA, there's always a maximization. I've always been arguing that, well, once we've got Q, all you need to do to pick actions is to maximize over A, and you pick the action with the highest Q, and you're done. You found the best way to behave. But what if that maximization is itself prohibitively expensive? What if you've got a trillion actions or a continuous action space? What do? This is actually quite common. If you've got a robot, it operates in a continuous action space of talks and so forth. If you're trying to, solve an internet-based problem where you're trying to create the perfect advert to show to your users, actually creating that advert might have many, many different components that you'd like to move around, and you'd like to make a sequence of adverts that you show that actually maximize your income with that user. This is a vast action space. So what do? Well, you can solve this complicated maximization at every step, or you can use policy-based methods where you just adjust the parameters of your policy directly and you never have to solve for this max. It's like you're incrementally starting to understand what the max will be rather than estimating the max directly every step. And the third reason that you might want to consider these policy-based methods is that they can learn stochastic policies. And in the next couple of slides, we'll see why that can sometimes be a good idea. So disadvantages. So the main disadvantage is that naive policy-based reinforcement learning can be slower and higher variance and less efficient than value-based methods. I think the way to think of this is that value-based methods, when you use the max, are extremely aggressive. It's like this max in one step is trying to improve your policy in the direction that absolutely pushes you all the way to what you currently think is the best policy. Whereas policy gradient methods just take a little step in that direction. They smoothly update in that direction, which makes them more stable, but also sometimes less efficient. And sometimes actually computing that step to take, that gradient, if you do it naively, it can be higher variance and slow down the whole algorithm. But we'll see later how to get the best of both worlds by including a value function. And in practice, you may want a value function as well, which can add to the complexity of the algorithm a little bit. And just the flip side of the point which was made earlier, sometimes there are examples like we discussed in Breakout where a policy can be more compact, but it's also conceivable that there are cases where a value function gives you a very nice compact representation and gives you a more direct way to learn the solution to your MDP. Okay, so let's consider, how can it be the case, why would we ever want to learn a stochastic policy? Ultimately, aren't we just maximizing? Don't we just want the thing which maximizes? Don't we want to maximize our reward? And if we're always maximizing reward, intuitively you might think a deterministic policy should be good enough, because a deterministic policy is always something, you can always find it, maximizing something can be a deterministic process. But there are cases where it's actually desirable to have a stochastic policy, and we'll see two of those now. So the first example is rock, paper, scissors, or Rochambeau, or it has lots of different names depending where you're from and how you play this. But it's just the game where you show paper, scissors, or stone, and scissors beats paper, rock beats scissors, paper beats rock. And so you probably know this, but if you were to just play this deterministically, any deterministic strategy is very easily exploited. If I always play rock, and I start to play against you, you'll very quickly figure out that you should just play paper, and I'll lose every single time. And in fact, the only optimal policy in this domain, in terms of a Nash equilibrium, which is the game theoretic notion of optimality, the only optimal policy is to play actually uniformly at random. Anything else can be exploited, because if you play one choice more often, your opponent will learn to exploit that. So this is an example where the optimal behavior is actually stochastic. A stochastic policy is necessary. A second example is when we have state aliasing. So this comes up when the Markov property doesn't hold. So we might be in an MDP, but it might be that we lose the Markov property. We get partially observed environment. So if you remember this distinction between fully observed and partially observed, what's going to happen now is we're only going to see certain things about this environment, or equivalently, we're only going to use features which give us incomplete information about where we are in this environment. So consider this little problem here. So as you might guess, getting to this treasure is good, and getting to the skull and crossbones is bad. And this is just a little grid world. You get to move around it, go north, east, south, or west. And the question is, what's the best that you can achieve in this domain? Except we're going to restrict the way that we can create our value functional policy to use the following features. So we're going to consider features which basically tell us they're features of both the state and action. So they're going to be features that say things like, is there a wall to the north of me? Is there a wall to the south of me? In between these squares, by the way, if they're adjacent, there's no wall between them. So this is like, is there an exterior wall? And the other part of the feature is there an exterior wall to the north, and I'm moving to the east? And that would be a feature of my state and action pair. Okay? So we're going to consider features like this. Is there a wall to the north when I'm going east? And we're going to consider all such features, like is there a wall to the west when I'm going south, and all kinds of things like this. And we want to know, what's the best I can do using either value-based or policy-based reinforcement learning. So in each case, we're going to approximate either the value function using these features, and it doesn't matter what the function approximator is. This could be linear, it could be a complicated neural network, it could be your favorite thing. The question is, what's the best that could be done in principle? And we're going to compare it to policy-based reinforcement learning, where we parameterize a policy using some function of these features. And the question is, which will do better? So does anyone have any intuition into this? I'll show it over the next couple of slides, but just have a quick think if you can figure out what's going on. Yeah?
You're not going to be able to tell the difference between those two grey squares with the features.
Right. So the point was that these two grey squares are aliased. There's no way to tell the difference between these two grey squares using the features that you have. Like if you're here and going west, or if you're here and going west, those two things look exactly the same to you. Because you've got a wall to the north, you've got a wall to the south, and you're going west. So your feature vector will be identical, and you can't tell the difference between those two states. So as a result, if you use a deterministic policy, then you have to pick the same action in those two grey states. A deterministic policy, which is parameterized in terms of those two things. And so imagine that you learn a value function now. The value function for these two states has to be the same. And if you act greedily with respect to that value function, you'll either go west all the time, or you'll go east all the time. Okay? And so this greedy idea of generating a deterministic policy, or even a near deterministic policy, would basically lead to the following behavior, which is if you're on this side of the map, you would oscillate backwards and forwards forever if you're using greedy, or for quite a long time if it was epsilon greedy, and you'd never reach the treasure, or take a very long time to reach the treasure. If you use a stochastic policy, then things are much better, because we can optimize our policy so as to choose a policy that goes east or west with 50-50 probability here. So now, if we're in this grey states, we'll just randomly pick a direction, and if we find ourselves over here, well, sometimes we'll go left, but sometimes we'll go back right, and then we'll be pushed down to the treasure. So in just a couple of steps, we're likely to reach the treasure, compared to a value-based method, where if we were to act greedily with respect to our value function, we would end up taking, in certain cases, a very, very long time to reach the treasure, possibly forever. Okay, So the summary of these couple of slides is to say that whenever state aliasing occurs, a stochastic policy can do better than a deterministic policy. So we had a theorem early on in the course which was that there's always a deterministic optimal policy for any MDP. But that's for a Markov decision process where you have, that was in the table lookup case, where we have the perfect state representation. The moment you have state aliasing, so you're partially observed, so if you're in a partially observed Markov decision process, or if you're function approximated, the features that you use limit your view of this world, which is equivalent to being in a partially observed MDP, then it can be optimal to use a stochastic policy, in which case policy search methods can do better than these value-based methods which just act greedily. Okay, so let's talk about how to optimize a policy. So what does it mean to optimize a policy? Well, we need to know what the objective should be. So here's 3 different objective functions we might choose. We want to know how good is this policy. The first choice is, so we're going to consider some parameterized policy with these parameters u, and we want to know essentially what's the best u. So the first case we're going to consider is, if we're in an episodic environment, we're going to consider the starts value. This basically says, if I always start in some state S1, or if I have some distribution over start states S1, what's the total reward that I'll get from that start state onwards? Okay? So this only works if there's this notion of a start state. So if there's a start state, you might say, really, the thing I really care about is I want to find the policy which, when I dump my agent down in the start state, I start my game of Atari and I play it all the way to the end, it gets the most score. Or we could use the average value, and this is something we could do in a continuing environment. So now, in an environment which just goes on forever, there might not be a start state. So now we might want to say, well, let's consider the probability that we're in any state. This is the stationary distribution. This is the probability that we actually end up in any state under our policy pi, times the value from that state onwards. So it's like averaging over the values of all states. So I might be in state 1 and get 10 units of reward from that point onwards, or I might be in state 2 and get 20 units of reward from that point onwards. And so we might average over those and say, well, the objective is maybe 15. Or we might consider another formulation, which is the average reward per time step, which is similar, but we might say, well, what we really care about is just, let's consider some continuing environment. I'm going round and round and round, and all I care about is to make sure that per time step I'm getting the most reward. So we're not summing these rewards over time, we're just saying we're going to take the average of my immediate rewards over the entire distribution of states that I visit. So this is basically saying the objective is there's some probability that I'm in a state, there's some probability I'll take an action from that state under my policy, and this is the immediate reward that I'll get at that step. And what we care about is getting the most reward per time step. That's another way of saying to extracting the most juice from my environment. I get the most reward per time step. This relates to the average reward formulation that was like an extra for lecture 2 that you find in the notes. Okay, so it turns out that, fortunately for us, that exactly the same methods apply to all 3 of these. They turn out to, the policy gradient is essentially the same for all of them. The only thing which differs is the definition of this distribution term here, like what's the probability that I'm in some state S. And they're just rescalings of each other. So they turn out to basically follow the same gradient direction. And so we don't really need to worry which of these we're following because we end up with the same policy gradient. So now what we're going to consider is trying to optimize one of these objectives. So we're going to pick one of those 3 objectives. And we're going to say what we want to do is to find the u, find the parameters that maximize this objective function. So find the u such that when you drop your IBO robot down, your IBO will walk as fast as possible. And so how can we do that? Well, there's lots of familiar approaches to optimization. Hopefully you've come across some of these. Optimization methods are classically divided up into gradient-based methods and gradient-free methods for optimization. So if you don't have access to the gradient, there's some algorithms you could use for optimization, like hill climbing or simplex method, where you've kind of got a triangle that you flip over and over and over as it folds its way down the hill, sometimes called the amoeba or Nelda-Mead. Genetic algorithms, these are all optimization methods that you could throw at a policy search problem and try and find the best policy which maximizes one of these objective functions. But typically, the reason people consider gradient-based methods is if you have access to the gradient, you can almost always get greater efficiency out of your optimization method. And some of the familiar methods for doing this are things like gradient descent, conjugate gradient, quasi-Newton methods. There's another large family of methods that make use of the gradient information to gain greater efficiency, because you know this gradient points you in the direction of greater reward, points you in the direction of how to do better in this MDP, rather than having to blindly try things by trial and error and figure out which of those is the best. So we will focus on gradient descent, the simplest instance of this. Of course, once you understand how to do gradient descent, you should also understand that this can be extended to other methods, for example, second-order methods, quasi-Newton. All of these things are possible, but I think the ideas are best illustrated and often work most effectively with the simplest case, which with very little computation, you can get a great deal of effective reinforcement learning out of this. We're also going to focus on methods that exploit the sequential structure, by which I mean we're not just going to do blind optimization like a genetic algorithm, where you have to throw your robot down, wait until the end of its lifetime to get one number that pops out of it that says, I achieved X in my lifetime. We would rather break open the trajectory, see that partway through this trajectory it had achieved some sequence of states and rewards, and make use of that sequence of states and rewards to do better than waiting all the way until the end, until this thing dies, before you can actually optimize it. And so we'd like to learn within the lifetime of an agent. Okay, so we'll start with the very simplest version, which is finite difference policy gradient methods. So let's begin by this familiar idea of what policy gradient is. So in the last lecture we considered gradient descent, because we had something like a mean squared error, and we were trying to minimize the error. In this lecture we're going to consider gradient ascent, where we have an objective function, which is something like how much reward can I get out of this system, and we want to make this thing higher. We want to basically ascend our objective function. So we can imagine that there's some surface that says, for any policy parameter, so imagine that these are two different policy parameters, and there's some surface defined by those two different policy parameters, and they might be parameters of how my IBO walks around, and we're going to adjust those policy parameters in the direction that gets us a faster walk, for example. And this surface has some shape, and the gradient basically points us uphill in the direction of steepest ascent uphill. And so all that says is mathematically what we're going to do is adjust our policy parameters a little bit in the direction of the gradient of this objective function. And the gradient of this objective function is just the vector of partial derivatives. So it's the vector that says, along this direction here, how much progress can I make by adjusting this parameter? Along this other axis here, how much progress can I make? And we just move things in the direction that maximizes our progress and makes the most possible difference in an infinitesimal radius around where I am now. So we're adjusting the parameters to get more juice out of our environment. Okay? So the simplest way, this is the naive approach, the numerical approach. If you had no way to understand what the gradient was, you could just do the following. You could basically look at your objective function and estimate this thing numerically by saying, well, if I just perturb my parameters a little bit, I could perturb them in each dimension. I could say, well, what would happen if I changed my policy parameter along the first axis a little bit? And I would look at the difference between the objective after I perturbed it and the objective before I perturbed it. That would be an estimate of the gradient in that direction. And then we do that for each dimension separately, and that gives us a numerical estimate of the gradient. This is a little bit naive because you need an awful lot. If we're working in high-dimensional space, imagine your policy is a neural network with 1 million parameters. Now you need to do 1 million different evaluations of your policy. You need to perturb it in all those different directions to get an estimate of what the gradient is in that direction. There are techniques that use random directions, like SPSA, which reduce the number of samples you need to take, but they still are very, very noisy. And so it takes an awful lot of computation using these methods to actually even get one estimate of the correct gradient. But nevertheless, it's simple. There's no, this is if you really can just perturb your policy and try again multiple times, you will get something which points you in the correct direction eventually. And so it can work for arbitrary policies, and one big advantage is this works even if you've got some non-differentiable policy. Like someone gives you the program for your robot and tells you, here's some parameters for your program, but we don't know how to differentiate them. You can still adjust it by following this process. So I've been talking about an IBO, so let's make that concrete. So it turns out that in RoboCup Soccer, things have got a little bit better, but I think it's roughly still true that with the IBO League in particular, this is one of the leagues of RoboCup Soccer, they have these little dog robots, the IBOs, running around trying to score goals against each other. So it's quite a fun competition. But the thing which determines which team wins is basically how fast you can get your IBO to run. If it can walk faster, you basically are able to just take the ball and move it faster down the field. And so the team with the fastest IBOs historically has always won. And so it's become an interesting machine learning challenge to make the IBO gate more efficient and make it run faster. And so the IBO gate is basically controlled by 12 different real numbers, which are sort of shown in this diagram here. It doesn't really matter what they are. But the goal is to adapt these parameters now. And the first people to do this, Peter Stone et al., they did it by finite difference policy gradient, just like we just described in the last slide. And then what they did was they basically just ran these robots backwards and forwards along this field and measured how long it took them with each gate. It gave them a few walks up and down and measured how long it took. Did that for each of these 12 dimensions separately. And then, so you have to run it up and down to get one dimension, run it up and down again 12 times to get just one gradient update. You adjust your parameters in that direction and iterate this process until your grad students collapse of exhaustion. And so they did this, and let me see if I can pull up some videos. Okay. So this is at an early stage before it's really been trained, and I think what the main thing to notice is that it slips a lot. That this thing is really dependent on the ground which it's on, and it tends to slip an awful lot. And over time, it starts to learn something a little bit better. This one. Uh-oh. Oh no, there we go. Let me try that again. I think that was just an artifact. No? But you can see it's learned this much better gate that deals with the slippiness of the surface much better, and it can move much, much faster. So this was just by adjusting the parameters in the direction of the gradient in a very naive, straightforward way, and some limited number of iterations were sufficient to make progress in this domain and actually figure out a reasonable gate. Now, if you move to higher dimensions, these numerical methods tend to collapse. And so what we'll consider for the rest of the class is how to analytically compute the gradient so that you don't have to laboriously compute this gradient separately for each of your dimensions. Okay, so we'll start with the simplest approaches, no value functions yet. That's the Monte Carlo approaches, and then we'll come back and we'll bring value functions back into the picture. Okay, so we're going to use the following idea, which is we want to compute the policy gradient analytically, and what we're going to assume is that our policy is differentiable. It doesn't actually technically have to be differentiable everywhere, it only has to be differentiable when it's actually picking actions. So if you have some non-differentiability but you're not actually ever picking that action, that's okay. We're also going to assume that we know the gradient of our policy, that we're in control of our policy, something like again, it could be a Gaussian policy or a softmax policy, we'll see some examples, or a neural network, and we know the gradient of this thing because we've created it. And what we're going to use is a trick called likelihood ratios. And the likelihood ratio trick, I'm just going to put it up in isolation, because what we're going to see is pretty much for the rest of the course, this magic gradient of the log policy term is going to appear. And I think it's useful to understand why this gradient of the log appears, because otherwise you'll just be scratching your head saying, why are we suddenly looking at the log of the policy, not the policy itself. And it basically comes up just from this following likelihood ratio trick, where what we're going to want to do is we want to take the gradient of our policy, we want to understand the policy gradient, and we're going to want to take expectations of that thing. And so the way we do that is we basically note that we can multiply and divide by our policy without changing it, and that this term over here on the right, the gradient of the policy divided by the policy, is equal to the gradient of the log of the policy. Okay? So that's just straightforward calculus. And this term over here is a very familiar quantity from statistics and machine learning. It's sometimes called the score function. But if you were doing something like maximum likelihood learning, this is the term which would come up. If you were just trying to maximize the likelihood of some action A, which someone gave you, you would follow this gradient. This is the thing which maximizes the log likelihood. And so the way to think of this term is this is the thing which tells you how to adjust your policy in a direction that gets more of something. So if you were to tell it the right action and you were doing supervised learning, you would plug in exactly this term for some particular supervised action here, and that would tell you how to get more of that particular action. So this tells you how to adjust your policy in a particular direction to achieve more of something that's good. And so we're going to use that, and what we see now is that by basically rewriting this gradient in this way, we're able to take expectations. Like computing the expectation of this thing is hard, but computing the expectation of this thing is easy because we have this policy here, and this is actually the policy we're following. And so we can take an expectation of this term because this is something we can actually sample from. This is the policy that we're actually following ourselves. So we'll see that in a minute. But just before we do that, let's consider this score function and understand what it looks like for two common examples. So perhaps the simplest example you should have in your mind, which we use for discrete actions, is the softmax policy. So the softmax policy is basically something where we want to have some smoothly parameterized policy that tells us how frequently we should choose an action for each of our discrete set of actions. So this is an alternative to something like epsilon greedy, or and the idea is to basically say what we're going to do is we're going to take some features, we're going to form some linear combination of features, for example, and we're going to consider that as like this some kind of value that tells us how much we'd like to take an action. So we've got features of our action in our state, we've got some parameters for those features, and then we weight those features by some weight, and we add it all together, and that tells us how much we desire that particular action A. And then what we do is to actually turn that into a probability, we just exponentiate it, and we normalize. So the idea is that the probability that we actually pick an action is proportional to the exponentiated value that we get when we take a linear combination of these features. So this is called the linear softmax policy. So a softmax in general is a policy that's proportional to some exponentiated value. And you can choose those values to be anything you want. And here we're just parameterizing those values in the simplest possible way by using a linear combination of some parameters with our features. So this is a very straightforward way to parameterize a policy in a discrete domain. So imagine we're doing Atari, and we want to know, should I go left or should I go right? Well, we'd have some features of going left, and we'd have some features corresponding to going right. We would weight each of those, and whichever one scores more highly when we make this weighted sum would get higher probability when we actually come to pick these actions. And now what we're going to try and do is find the gradient of this thing. We want to know, well, how do we adjust this thing so as to get more of the good things? So we need to know the score function, and the score function is very intuitive for this softmax. The score function, the gradient of this locked policy, is just the feature for the action that we actually took minus the average feature for all the actions we might have taken. So it's basically saying, how much more of this feature do I have than usual? And that's the score function. And so what we'll see is when we start to do these kind of policy gradient algorithms, what we'll actually end up doing is saying, if a feature occurs more than usual, that's what this thing is telling us, if it occurs more than usual, and it gets a good reward, then we want to adjust the policy to do more of that thing. Okay, so this is the softmax policy. I just want to give one more example of policy, which is the Gaussian policy. So in a continuous action space, like the IBO example, the commonest policy to use is a Gaussian policy. And what do we do with a Gaussian policy? Well, we basically just parameterize the mean of this Gaussian, and then you have some randomness around that mean, some variance around that mean, that says most of the time I'm going to take this mean action, that's given by, say, a linear combination of some features. But sometimes I might take some deviation from that mean, and there'll be some variance like sigma squared, which could also be parameterized. You could have a variable variance. But the simplest case is to say now the action is selected according to some normal distribution with mean mu of s, where this might be a linear combination of our features. Like before, we've got features of our state and some weights for those features, and some variance parameter. So basically we get to pick the mean, and then we just add some noise to that thing to make it stochastic. And so if we were using a Gaussian policy, what would this score function look like? Well, the score function is basically, again, this tells us how to get more of a particular action. And here, again, we have something very similar to the last slide, where this tells us this is the action we actually took. This was our action A. And this is the mean action. This is the mean. So we basically want to know, let's take the action we actually took minus the mean. That tells us how much more than usual we're doing a particular action. Multiplied by the feature. And then we just scale that by the variance. So in both of these cases, the score function takes this form of sort of how much more than usual am I doing something. And that's quite intuitive when we start to look at these policy gradient updates. Okay, so that's just to give some intuition for what these score functions look like. Now let's talk about the actual policy gradient, this analytic policy gradient. And to do this, I'm just going to derive it for the simplest possible case, and homework, if you like, could be to extend this to the full MDP case. We'll talk about what it looks like, but I won't derive it for you. And the special case we're going to consider are one-step MDPs. So what do I mean by one-step MDP? I mean that you start in some start state S. You get to take one step, and you get one reward. That depends on where you were and what action you took. But then the episode terminates immediately. So there's no sequence in this case. It's just a one step, and then you're done. And you get some reward, and the goal is to pick your actions so that you maximize that reward. And the right thing to do might depend on the state and the action. So we'll see later this is also called, in a subsequent lecture, as a type of contextual bandit. And so now, if we were to try and solve this, we want to find the policy gradient. We want to understand how to adjust our policy parameters so that no matter what state we're in, we pick an action that's good. We want to adjust our way of picking actions so as to get more rewards. And the way we're going to do that is to start off by picking our objective function. So in this one-step case, all three of those objective functions we talked about become the same, essentially. And so our objective function is just to the expected reward under our policy. So we want to find the parameters which give us the most expected reward. And so we want to find the gradient of this thing and ascend the gradient of this thing, which will give us more expected reward. So if we're thrown into any state and we pick an action according to our policy, we want an expectation that to give us the most reward. And so the way we're going to do that, so let's just expand this out. So this is the expectation over the state that we start in, and this is the expectation over the actions that we pick under our own policy. So this is the expected reward. And now we're just going to plug in the likelihood ratio trick. So we're going to take the gradient of this whole thing. We want to know the gradient that gets us more reward. So the gradient of this whole thing, basically, the only term which depends on u is our policy. So the gradient of this whole thing, we could push the gradient right in to the gradient just of this term here, and expand that using our likelihood ratio trick. So this whole thing, the gradient becomes now the policy multiplied by the gradient of the log policy multiplied by the reward that you get. And so this is, again, now an expectation. That's the whole point of using the likelihood ratio trick. We start with something which is an expectation, you take the gradient, and you recover something which is still an expectation. So this thing is an expectation under our policy. So this is the expectation under the start state, an expectation under the action that we pick of the gradient of the log policy multiplied by the reward. So it's just the expectation of the score times the reward. So after all that, we've basically come back to something very simple, which tells us that if we want to increase our objective function, if we want to get more reward, we just need to move in the direction that's determined by the score times the reward. Okay, and so again, this tells us how to adjust our policy so to get more or less of something, and this tells us whether it was good or bad. So if you have a really big positive reward, you want to move more in the direction that gets more of that thing. If you have a really low negative reward, a really large negative reward, you want to move in the opposite direction to your gradient. Okay? Any questions? Stunned silence. Okay. So, yes.
Can I just ask, this is model 3, right?
Yeah.
And we have the capital R, which means that we know rewards and everything.
Okay. So notation. This capital R is the random reward, the actual reward that you experience. This curly R is the reward function for the MDP. So we've expanded this in terms of something which actually is described in terms of the dynamics of the true MDP, but we brought it back again to an expectation where we only need to look at the sample reward that the agent actually experiences. So this is completely model free. So model free, what this means is if we want to estimate this expectation, we just take an action from a given state, we compute the gradient of this log policy, which we know because it's our own policy, and we multiply it by the reward that we actually experience. And that gives us a gradient step, and we follow that gradient step. So it's model free. Good question. Okay, so we want to do the same thing in MDPs, multi-step MDPs, not just these one-step things. And to do that, we actually just need to do one trick, which is to replace this instantaneous reward that we had. So we were multiplying the score by the immediate reward. And to do a multi-step MDP, all we need to do is actually replace this immediate reward with the value function, the long-term reward. And that actually turns out to be the true gradient